In part 2 of our calculations for this example, we have to figure out the mass of the products that can be produced. We figured out in the previous video that the 2.50 grams of aluminum bromide is going to limit the amount of everything that happens. So the masses of all the things that are present at the end of the reaction will be based on using up the 2.500 grams of aluminum bromide. We're going to use that mass, and we're going to calculate the mass of aluminum carbonate that we can make and the mass of the sodium bromide that we can make. So to look back at our container, our initial container has the 2.500 grams of aluminum bromide and the 3.750 grams of sodium carbonate, and they are dissolved in water. So based on our calculations, we figured out that 1.490 grams of sodium carbonate is needed, and we had the 3.750 grams of sodium carbonate. So if we use up the 1.490 grams, that leaves us with 2.260 grams of sodium carbonate when the reaction ends. There won't be any of the aluminum bromide because all of it will be used. But in this container with the sodium ions and carbonate ions is going to be solid aluminum carbonate and dissolved sodium bromide. So we're going to do the calculations to figure out what those amounts will be. So what is the mass of each product that can be produced? So to do our calculations, we have to start with our measurement. So you always start with the measurement. So you're going to write down the 2.50 grams of aluminum bromide. You want to then convert that into moles. To convert it into moles, we're going to divide by the molar mass of aluminum bromide. That will get us into moles of aluminum bromide. But if we want to calculate how much sodium bromide we make, then we use the coefficients from the reaction. The coefficients are 6 moles for sodium bromide and 2 moles for aluminum bromide. So that's a 6:2 ratio. This will allow us to calculate the moles of sodium bromide that will be produced from the 2.500 grams of aluminum bromide that reacts. But we want to see what the mass would be so we can get the mass relationship. So the 2.500 grams of aluminum bromide, once it all converts into sodium bromide, the mass would work out to be 2.894 grams of sodium bromide. So this is the theoretical mass of the product sodium bromide. You get this by multiplying across the top, and then you come back and you divide by the 266.694 and the 2 moles. All the units will cancel except for grams of sodium bromide. You do the same calculation to figure out the mass of the aluminum carbonate. So starting with our 2.500 grams of the aluminum bromide, you have to get it in terms of moles so that you can see the mole-to-mole ratio between the aluminum bromide and the aluminum carbonate. The coefficient for aluminum carbonate is a 1. The coefficient for the aluminum bromide is 2. We then will multiply by the molar mass to convert from moles of aluminum carbonate into grams of aluminum carbonate. When you multiply across the top and you divide by the numbers in the denominator, you end up with a mass of 1.097 grams of aluminum carbonate. So those are the two theoretical masses for each product. Molar mass to get to moles of your starting material, mole-to-mole ratio, which are the coefficients from the balanced reaction to convert from one substance to another, and then the molar mass of that substance so that you can figure out what the mass of that substance would be. So these two are the amounts that would theoretically be present when the reaction ends. So if we bring back our before and after picture, in that container we have the 2.260 grams of sodium carbonate that remains. we have now calculated that also in that container we should have 2.894 grams of sodium bromide and 1.097 grams of the aluminum carbonate. So this is the before, the mass of the chemicals, and this is the after, this is the chemicals that remain, and there will be 0 grams of the aluminum bromide because it is what is all used up because it's the limiting reactant. One thing that you can do to prove that long calculations like this are correct and that you have a good understanding is you can see if it obeys the law of conservation of matter or law of conservation of mass. Matter would be when you're thinking about the substances, the elements involved. And mass when you're just thinking about the quantities. And so just looking at the quantities, you can add up the mass of the chemicals that are in the beaker before, and when you add those two together, you get 6.250 grams total before the reaction. When you add up the masses of the chemicals that remain after the reaction ends, then it adds up to be 6.251 grams total. Sometimes this happens where the two masses, they look about the same, but the very last digit, that estimated digit, is off by 1. This occurs usually when you have 3 different measurements that you're figuring out because each of the measurements along the way involved rounding to the last digit. So if you round 2 of them up and you leave 1 of them the same, sometimes that results in a number where the last digit is 1 more than the original. Or vice versa. If you don't round any of them, then sometimes it'll be the total after will be 1 less in the last digit. But this does not show, because these don't equal, it doesn't mean we did anything wrong. It just means these involved calculations. And so these are equal to each other. Again, that last digit being off is just because of the calculation. So this shows that we have done the calculation correctly, we have accounted for all of our chemicals, and we know how much remains after the reaction is over.